This video covers Chapter 11, Section 3, about inference with several sample designs. We'll start by looking at the similarities and differences between several sample and two sample designs. We'll talk about variation among means or within groups. We'll introduce the F statistic as the ratio of variation among the means and within the groups. And we'll talk about the role that sample size plays in performing this hypothesis test. Additionally, we'll introduce the ANOVA test, that's analysis of variance. We'll talk about formulating the hypotheses, creating the table and the test statistic, and finding the p-value. We'll look at the first step in statistics in practice with displays and summaries. We'll take a look at how to read ANOVA output, and we'll give a few guidelines for the use of ANOVA. Among the four stages of statistics, we are in statistical inference, and we're looking at several sample study designs for relationships between categorical and quantitative variables. Remember that with a categorical, explanatory, and quantitative response variable, there are three main types of study designs that we might look at. Each has its own separate inference method. For a paired study, we reduce to the differences and perform one sample t-tests. For two sample studies, we use a two sample t-test and two sample t-interval. The two sample test looks at the difference between two means. Finally, we'll talk about the several sample design, which uses a new distribution called the F distribution. Here we're looking at a difference among means. Before we jump into that, a quick grammar note. The word between implies that we're looking at only two things. The word among implies that we're looking at three or more. That's the important difference here, and it's one that we're going to exploit several times. So remember that when we have a several sample design to display and summarize data, with a display we use side-by-side box plots. One box plot for each group that is represented in the categorical variable, and you want to make sure that every box plot has the same vertical scale. To summarize, we can either compare the 5 number summaries, which are related to the box plots, or we can compare the means and standard deviations. It's this latter one that we're going to use for inference. Let's quickly look at some notation. Here, capital I represents the number of groups compared. So if we were talking, for example, about Wofford students, we might have first-year students, sophomores, juniors, and seniors. Those are 4 groups, so in that case, capital I would be 4. So our notation for the sample sizes in each of those individual samples will be N1, N2, all the way up to N sub I. All those numbers together, when you add them up, you get a number we're going to call capital N. That's the overall size of the big sample. Remember, the categorical explanatory variable takes our big sample and breaks it down into smaller samples. The means in the sample we'll denote as before, X bar with a subscript that corresponds to the group number that we're looking at. The mean of the overall sample, that is if we lumped all of the categories together, we'll still continue to denote that with X bar. The population means, we use mu with a subscript corresponding to the group. And for the standard deviations, as before, we'll use S's for the sample standard deviations and sigmas for the population standard deviations. Now let's look at similarities and differences between two sample and several sample inference. Here's how they're similar. The test statistic for two samples, that's T, and for several samples, that's F. What these statistics do is it takes the difference among or between the sample means and standardizes it. They take sample size and standard deviations into account. But the difference is that F, the several sample test statistic, focuses on squared differences of means in the numerator, F is a fraction, and squared standard deviations in the denominator. The procedure that we use to perform hypothesis tests is called ANOVA, which stands for Analysis of Variance. If we have two groups with equal sizes, so if we're looking at, for example, males and females, where the population standard deviations are the same, in that case, F, which is what we'll get using the ANOVA process, is equal to t squared, where that t comes from the two sample process. Additionally, the p-value that corresponds with that value for F and that value for t squared end up being exactly the same. So let's take a look at those two distributions. On the left, you see 100 values taken from a t distribution. So we would expect it to look somewhat like the t distribution does. Remember, that's bell-shaped and symmetric. And that's pretty much what this looks like. On the right, we've taken the values that we obtained on the left, those 100 values taken from the t distribution, and squared them all. What does that distribution look like? Well, one thing that we note is that when we square all those t values, the negative numbers become positive, the positive numbers stay positive. So we only get positive values for F. Since most of the t values were near 0 to start with, once we square, the new F values are mostly going to be piled up around 0. So since most of the values are going to be around 0 and we can only get something positive, that means that this distribution is going to be very strongly right-skewed. Notice that a value like 3, when it gets squared, becomes 9. So a really big t value becomes a really, really big F value. So let's take a closer look at the way these statistics, t and f, are computed. Remember that the test statistic is a standardization of the difference in sample means. It takes into account the size of each sample and the standard deviations of each sample. For a two-sample design, recall that this is how we compute t. Now here is our new f statistic. Now don't worry, I'm not ever going to ask you to compute this by hand. Let's dive in a little deeper. How different are the sample means? Notice in the numerator of t we have x1 bar minus x2 bar. That's the difference in the mean of the first sample and the mean of the second sample. When we compute f, we're looking at the difference between the mean of each, within each category, the mean of the first sample, the mean of the second sample, but we're comparing them to the overall total mean. That's what that x bar is, remember. That's the mean of what we would get if we took all the categories and lumped them in together. Now, how spread out are these distributions? The standard deviations of each sample appear in the denominator of the t statistic. They get squared and then added together after dividing by the sample sizes, and then we take a square root. In the f statistic, we also square the individual standard deviations, but notice there's no square root involved. This makes sense. Remember, in the numerator, we didn't have a square on the difference in means in t, but we do have a square on each of the difference of means for the f statistic. How large are the samples? Remember, N1 and N2 are the sizes of sample 1 and sample 2. They go into our computation for t here. In the f statistic, what happens is that the individual sizes of each group more or less cancel out. We've got an n1 in the numerator and an n1 in the denominator. Now I know these don't exactly cancel out, but they come pretty close. The n2's cancel, the n3's cancel, the ni's cancel. What we're left with is this big N, is the main factor. Remember, N is the total size of the overall sample. Now, what could make these numbers big? Well, if the differences in the sample means in the numerator are big, that's going to make T and F both bigger. If the standard deviations within each sample are small, that's also going to make both T and F bigger because they appear in the denominator. What about the size of the sample? The sizes of the samples are in the denominator of the denominators. That means that they will increase the value of the fraction overall as they get bigger. Let's look at those spreads. Remember, when we compare side-by-side box plots, here we have three categories. The box plots on the left side of the bar, that's the ones over here. We want to compare those to the three on this side. Notice that the three on the left have the same means as the three on the right, so the same centers. What's different is the spreads. For which of these scenarios, the one on the left or the one on the right, do you feel like the difference among the three means is more significant? Well, it's the one on the right. Because the spreads are smaller, there's less overlap. If you look over here to the one on the left, if you look in group 1, that mean is within the middle 50% of the second group. The mean of the second group is within the middle 50% of both the first and the third group. And the mean of the third group is within the middle 50% of the second group. So overall, there's a lot of overlap among these three boxes. But if you look at the scenario on the right, there's a gap between all of the boxes. That convinces me that there's a real difference. So that's why smaller standard deviations result in bigger test statistics and therefore smaller p-values. Now in this same scenario, we've got the one on the left with big spreads, the one on the right with small spreads. In which of these are we more likely to reject the hypothesis that the population means are equal? Well, again, it's the one on the right. Because on the right, we have smaller standard deviations, which means we have a larger F statistic, which means we have a smaller p-value, which makes us more likely to reject the null hypothesis. The one on the right will probably conclude that the population means are different. Now let's take a closer look at this F statistic. The numerator of F is a measure of the variation among the groups, how the groups differ from each other. We get at that variation among the groups by looking at how far each individual group's mean differs from the overall mean of every group. In the denominator is a measure of the variation within each group. That's why we see the sample standard deviations appear there. So let's look at the numerator a little more closely. Here I is 3 because we have 3 groups. Big N is 15. That's because we have 15 data points overall. And you can see N1, N2, and N3 are all 5. So we're looking at 3 groups of 5 individuals each for a total of 15. The means of group 1, 2, and 3 are 3, 4, and 5 respectively, and they all have the same sample standard deviation. So here's what goes into the numerator. First is the SSG, that's the sum of squared differences among the groups. That's where we take the sample size, N1, times the difference in the mean for group 1, that's 3, and the overall mean, that's 4, and square it. Plus, again, the sample size is 5 in group 2, times the mean of group 2, which is 4, minus the overall mean, which is also 4, and we square it, and so forth. So the SSG is 10. Next we have the DFG, that's the degrees of freedom for groups. The degrees of freedom for groups is always I minus 1. So here we had 3 groups, we subtract 1, we get 2 degrees of freedom for groups. Finally, we have the MSG, that's the mean squared differences among the groups. The MSG is the SSG divided by the DFG. That's how we get the numerator of the F statistic. Now, in both of these two scenarios we've been looking at, which we've decided are pretty different, the numerator of F is the same. Remember, the numerator does not take spreads into account, only the means. Since the means on the left and the means on the right are the same, we don't expect to get a different number. Now let's look at the denominator of F. Here we have the same data. Remember, the denominator is a measure of spread within the groups. Here are the components that go into the denominator. First is the SSE, that's the sum of squared error within each group. The sum of the squared errors is the one less than the size of the sample in each group. So that's the 5 minus 1. Remember, there are 5 individuals in group 1. So we'll subtract 1 from that, and we'll multiply it by the sample standard deviation squared. We do that for each group, and we get 30. Next, we need to compute the DFE. That's the degrees of freedom for error. The DFE is n minus I, so in this case it's 12. Finally, we get the MSE, that's the mean squared error within the groups. The mean squared error is the sum of the squared errors divided by the degrees of freedom for error. So it's the SSE over the DFE. In this case, it's 2.5. And that 2.5 is how we get the denominator. That 2.5 goes in the bottom. So the denominator of F will be smaller for the scenario on the right because the standard deviations are smaller. Because these numerators are the same, the one on the right has a much smaller denominator, so F, that's the ratio of those two, will be much bigger for the one on the right. So here's our F statistic. It's the MSG over the MSE, which we computed to be 5 and 2.5. That ratio is 2. This is a measure of the difference among the sample means, taking into account the spreads and the sample sizes. If this number is large, we'll reject the null hypothesis, that the 3 means are all the same. In that case, we conclude that the population means must be different somehow. So the big question now is, how large is 2? Does that count as being large enough? To answer that, we'll have to know how F is distributed. So let's say that we've got a standardized statistic of 2. If that's a z value, is that large? For a t value? For an f value? Well, for z, remember, 2 is kind of borderline. For t, it's not terribly large. It depends on the number of degrees of freedom. If n is big, it's borderline. If n is pretty small, 2 is not terribly big. For f, well, this depends on the degrees of freedom in the numerator and in the denominator, which is based on both the total sample size and the total number of groups. There's an entire family of f curves. All of them are non-negative and right-skewed. The spreads of the f values vary depending on the degrees of freedom for groups and the degrees of freedom for errors, which appear in the numerator and in the denominator of the computation. So let's look at an example computing some of these degrees of freedom. Consider these distributions. First, with I equals 5 and n equals 390, that means we have 5 groups and 390 total individuals. And let's look at f with degrees of freedom 2, degrees of freedom for groups 2, and degrees of freedom for errors 12. Now, what are the degrees of freedom for I equals 5 and n equals 390? And what are I and n if the degrees of freedom for groups is 2 and the degrees of freedom for errors is 12? Well, remember, the degrees of freedom for groups is 1 less than the number of groups, so that's 4. And the degrees of freedom for error is n minus I, so we get 390 minus 5, that's 385. Working backwards, if DFG is 2 and DFE is 12, we get that I must be 3, because the DFG is 1 less than the number of groups. And the DFE is the difference between n and I. We already know I is 3, so that means n must be 15. So in the scenario where DFG is 4 and DFE is 385, this is the distribution. The probability that f is greater than 3 for this distribution is about 2%. Is that good enough to reject a claim that 5 population means are equal? Sure. That would be considered a large f value and will reject the null hypothesis. What about if DFG is 2 and DFE is 12? In this case, since the p-value corresponding to f equals 3 is not less than 5%, in fact it's close to 9%, we would not reject the null hypothesis. What about if f were 2 instead of 3? Well, that would have an even bigger p-value. So in both cases, we don't reject the null hypothesis and we conclude that the means might be equal. So that's how we determine if f is large. Is 2 large for DFG equals 2 and DFE equals 12? That's the scenario we've been considering. No, it's absolutely not. So the earnings for the 5 sampled individuals from those 3 racial and ethnic groups that we've been looking at, the means were 3, 4, and 5 in thousands of dollars. The ANOVA procedure gave us an F statistic of 2, which is not large for these degrees of freedom. So what's our conclusion? These means do not differ significantly from one another. So in the population, it's possible that the means are equal. Now, what if we bumped up the number of people in each group to 12 instead of 5, with the same means and the same standard deviations? Well, in that case, we get an F statistic of 4.8, which corresponds to a p-value of 1.5%. What would we conclude in this case? Well, 12 instead of 5 is a much bigger sample. So we're going to reject the null hypothesis that the population means are the same, and we'll conclude that they must not be the same. Remember, larger samples give more evidence. Now, we've seen a picture of what the F distribution might look like. Let's talk about where it's centered. Remember that t has a standard deviation that's the typical distance of values from 0. Because it's standardized, it's approximately 1. Since f is what we get when we square t, that means that the mean of the f distribution is also approximately 1. So, consider this question. For all students at a university, are math SATs related to what year they're in? So how can we reformulate this? How can we frame this question in terms of parameters? In this case, means, instead of whether there's a relationship among the variables. Well, the way that we would do it is by asking, do the population mean SAT scores differ for first year, second year, third year, fourth year, and other students? If we ask, do mean earnings differ significantly for 3 racial and ethnic groups? To reframe that in terms of variables instead of means, we would ask, is there a relationship between earnings and racial and ethnic groups in the larger population? That's how we move back and forth between a relationship among variables or equality of parameters. I'm about to show you how to do ANOVA using your calculator. If you want to follow along with me, here's the set of data I'm going to use. I recommend you put these in L1, starting over here with anthropology, up through L4 for psychology. Go ahead and pause the video if you want to follow along. Alright, let's do analysis of variance using our calculators. Now, I have gone ahead and entered our data set into L1 through L4. You see them there. So we're ready to do the analysis. To get there, I'm going to go into my Stat menu. I'm going to go to Tests, and Analysis of Variance is at the very bottom, so I pushed up the up key to get there. When you push Enter, your calculator will just say ANOVA parentheses. At this point, you have to give it all the data. So our data were in L1, comma, L2, comma, L3, comma, and L4. I'll close off those parentheses and I'll hit Enter. It really is just this easy. Notice that we get everything that we want from the for our ANOVA table. We get the value of f and the p-value. We get the degrees of freedom, the sum of squares, and the mean of the squares. Remember, that's out of the numerator. And as we go down, for the error, remember this is for the denominator, we get degrees of freedom, sum of squares, and mean of squares. And we get a standard deviation reported. But remember, what we're most concerned about is that p-value. Since we're looking at number of credit hours taken by students in different majors, with this big p-value, we can't say that the credit hours taken is any different for any one group relative to the others. Now let's also do the ANOVA analysis using Excel. Here I've got the data entered into columns with the appropriate categories across the top. ANOVA is under Data Analysis. Remember, you need the Analysis Toolkit in order to get this. So I'm going to hit Data Analysis, and what I'm looking for is single factor ANOVA. So I'll click OK. It's going to ask me for the input range. I've already got it in there, but remember, you can just push the little button next to where it asks for it and just click and drag over the range of values that we want, and click that button again to expand it. These are grouped by columns, and I want to make sure I check that I have labels in the first row. Here it's asking for our alpha cutoff. Remember that we're using 0.05 for pretty much everything in this class. If yours is different, just change it here. I'm going to put my output right next to my chart, so I'm going to select output range, and I'm going to pick one of the cells that's real close by here. G2 looks good, and I'll click OK. I'm going to select all of these and double click up here to make sure we can see everything nicely. And you see everything we need to know. Here are our 4 groups, the counts within each group, the mean within each group, and the variance within each group. Further down, we see the complete ANOVA table, including the sum of squares for the variation between groups and within groups, the mean of squares between groups and within groups, with the degrees of freedom. Remember that the mean of the squares is just the sum of the squares divided by the degrees of freedom, and then we get f, which remember is the mean of the squares between the groups divided by the mean of the squares for the errors that's within the groups. So this number divided by this number is f, and we get our corresponding p-value. The last thing that's given here, called f crit, that's the critical value for f. Since we told Excel what we wanted for our alpha, this tells us the cutoff. If the f value were 2.975 or bigger, then we would have gotten a p-value of 0.05 or smaller. But doing ANOVA in Excel is really just this easy. This is the set of data that you'll use to answer the questions on the next few slides. Go ahead and pause the video and do what you need to do with the data so that you can perform the analysis. Now, to review, when we pose the null and alternate hypotheses about variables, the question is whether the variables are related or unrelated. That's true for all 3 of our relationship scenarios. When we rephrase the question about parameters, however, we're talking about whether we have equality. For categorical, explanatory, and quantitative response, the question is whether the population means are equal, or if it's a paired design, whether the mean of the differences equals 0. When we talk about a relationship between 2 categorical variables, we'll ask whether the population proportions are equal. And for a relationship between quantitative variables, we'll ask if the population slope is 0. More on those later. Let's focus now on the categorical, explanatory, and quantitative response. The null hypothesis for analysis of variance is always that the explanatory and response variables are not related. Equivalently, the null hypothesis is that every single one of the means is equal. Any difference that we see in our sample between the sample means, we can attribute to randomness, to chance. The alternate hypothesis is that the explanatory and response variables are related. How would we frame that in terms of our parameters? We would do it this way. The alternative is that not all of the means in the populations are equal. That is, that the difference that we see in our sample is too extreme to be chalked up to randomness. Now notice that the word not can appear in the null hypothesis or in the alternative hypothesis. It depends on if we're making a statement about variables or parameters. Be very careful with these. The placement of that word not is crucially important. Let's take a look at an example. Let's say that a reader writes in to a medical advice columnist asking, "Does everyone with Parkinson's disease shake?" If the doctor replies, "All patients with Parkinson's disease do not shake," is that right? I don't think so, because definitely some patients with Parkinson's disease do shake. What he meant was, not all patients with Parkinson's disease shake. Notice the placement of the word not in these 2 sentences. So when we're framing the alternative hypothesis for analysis of variance, remember the null hypothesis is that all of the means are equal. take a look at this alternative. Is that right? It's not. Remember, the null hypothesis says that mu1 equals mu2, and mu2 equals mu3, and equivalently, mu1 equals mu3. There are three things that it's claiming. All we know when we reject that statement is that at least one of the means is different from the others. So it could be that mu1 is not equal to mu2, and mu2 is not equal to mu3. It could be that mu2 and mu3 are equal, but that mu1 is different from those two. It could be that mu1 and mu2 are equal, and mu3 is different from those two. It could be that mu1 and mu3 are equal, and mu2 is different. Because there's so many possibilities, we'll typically just use words for this. We'll say that not all three of the means are equal. So here is a table that we'll often use to help us construct the F statistic. It helps us organize our calculations. Here, source refers to the source of variation, either the factor, which is the variation among groups. Remember, that comes from the explanatory variable. It's the number of different categories we have. That is related to the numerator. Error is referring to the spread within each individual group. That comes out of the denominator. Remember, the degrees of freedom computations are the DFG, that's the degrees of freedom among groups, is I minus 1, where I is the number of groups. And the DFE, that's the degrees of freedom for error, is N minus I, where N is the total number of individuals we're looking at. So DFG is I minus 1, DFE is N minus 1. SSG is a measure of the variation among the groups. It's the sum of the squares for groups. The SSE is a measure of the variation within the groups. That's the sum of the squares of errors. Those two numbers individually are really tedious to calculate. Everything else is pretty straightforward except for the p-value, which we'll need to use a calculator or a computer to get. Next, we get to the mean sum of squares, which we get by dividing the SSG by the DFG and dividing the SSE by the DFE. Finally, to get F, we take the quotient of MSG and MSE, and then we use software or a table to find the p-value. Now, I'll let you in on a little secret. Every time I hear the initialism MSG, I think of Madison Square Garden. If you put somewhere in your final exam that you like Madison Square Garden, I'll give you some bonus points. If you hear this, don't tell anybody else, because if more than half of the class puts it, nobody gets the credit. Now, let's look at some key values for analysis of variance. Let's say that we're looking at different classes of cars, sedans, minivans, and SUVs. Once we compute the sum of the squares among the groups and the sum of the squares for errors, we get 42 and 181.4. So what goes in the table? Well, DFG, that's the degrees of freedom for groups, is 2 because there are 3 groups. We subtract 1, we get 2. What's DFE? Remember, DFE is the total number of individuals that we're looking at. In this case, that's 8 plus 8 plus 12, that's 28, minus the number of groups. That gives us a total of 25. What's MSG? Well, remember, MSG is the mean of the squares for the group. We get that by taking SSG and dividing by DFG. We get 21. The MSE, that's the mean of the squares for error. We take the SSE and divide by the DFE, and that gives us 7.256. Finally, we can compute f by taking the ratio of those last two numbers, 21 over 7.256, and we get 2.89. So taking those numbers, what does the ANOVA table look like? Well, all we got to do is fill in those numbers in just the right places. We can use our calculator or use some software to find the p-value, and we get a p-value of 0.07. Not quite enough to reject the null, but you might call it marginally significant because it's pretty close. Now remember, if the sample means are very different, that means that f is large, and therefore the p-value is small, which means that we are likely to reject the claim that the population means are equal. That's the null hypothesis. If the sample means are relatively close together, that's going to make f smaller, and therefore make the p-value bigger, and lead us to not reject the null hypothesis, which means we might believe that the population means are all equal. So let's look at the large values of f. How large does it take to be a large value of f? Remember, the f is distributed according to the DFG and the DFE. As those numbers change, the shape of the distribution for f changes. For all of these, we're going to have to use software. We'll use our calculators, or we'll use computers. The p-value, remember, is where we finally draw the line. We use the p-value to decide what we're going to do, whether we're going to reject the null or accept the null. On the other end of that is looking at the displays and the summaries. So let's take a look at some box plots. Here's a relationship for students at a university. We're looking at whether math SATs are related to the year they're in. What can we learn from this box plot? Well, I can see as we move from left to right, that is younger students to older students, it seems that the centers of these distributions go down. So the suggestion is that younger students scored better in math. Let's look at the summaries for those variables. For the 5 groups, here are the means. Sure enough, as the level goes up, the means go down. The standard deviations tend to be around the same. They go from 60 up to about 90, but they're more or less clustered around 70. The sample sizes are big, especially for year 2. So let's say we're going to plug all that data into our calculators or into the computer, and here's what we get for our analysis of variance output. So is there a relationship between the groups? What do we get from this? Well, remember the null hypothesis is that all 5 means are the same. We got a p-value, that's the bottom line. Is that a small p-value? It sure is. Will we reject the null hypothesis? You bet. Can we conclude that all 5 population means may be equal? Certainly not. It looks like year and math SAT are related. So remember, the choice of the F distribution we use depends on the degrees of freedom both in the numerator and the denominator. Here's what the distribution looks like for I equals 5 and n equals 390. Notice that for f equals 3.87, the area in the tail to the right is 0.004. It's that p-value that lets us know if f is large. We're not always going to have a picture like this for every single possible combination of values for DFG and DFE. But here, again, we got a p-value of less than 1%. That means that f statistic must be pretty big. So looking at the math SATs versus years again, what issues should we think about before we jump to conclusions about relationships? Well, we have to worry about how the data were produced. So what are the things we need to think about when it comes to data production? We got to make sure that we have samples chosen randomly and independently from several populations, 3 or more. We have to make sure that we don't have to worry about confounding. If there are possible confounding variables, we need to separate those out. We have to make sure that our sample sizes are big enough to counteract any skewness we might see in individual samples. We have to make sure that the populations are at least 10 times the sample sizes. That's always important when we're looking at quantitative data. We need to make sure that the population variances are equal. That's one we haven't talked about yet for ANOVA. Let's look at that a little bit more closely. Remember when we were doing the 2-sample t-test, we had a situation where if the standard deviations in the populations were approximately equal, then we would pool our data together. That gives us more to work with and gives us more evidence. We had this rule of thumb that we could pool them together if the larger sample standard deviation was not more than twice the smaller sample standard deviation. Because for ANOVA, we saw on the last slide, we needed to assume that the variances were equal. That's the squares of the standard deviations. That means we need to make sure that we can pool the data before we can do ANOVA. So in the case of the math SATs, take a look at those standard deviations. Is it safe to assume that the population variances might be equal? Well, we can apply the same rule of thumb. We just have to look at the largest standard deviation and the smallest. If you double the smallest one, it's bigger than the biggest one. Equivalently, if you take the biggest one and cut it in half, it's smaller than the smallest one. But yeah, that's good. So we can assume that the variances are equal. So let's look at another example. Here we're looking at verbal SATs. Do we think that verbal SATs are related to the year? So here we have each individual group with their means and standard deviations reported, and we have the results of the ANOVA. Now, are all of our conditions met? And if they are, can we draw any conclusions about the relationship between those variables? The n's are all large enough, and checking the standard deviations, the bigger one, the biggest one, which is 124, is less than twice the smallest one, which was 65.87, so that's okay. So now we can look at our p-value. We see the p-value is 0.357. That's not small. So we have no evidence of a relationship. We do not reject the null hypothesis. Now let's look at those first two in our guidelines. The F-test found evidence of some relationship between math SAT and year. We got a really small p-value, but not verbal SAT and year. We got a pretty big p-value. Now a question, keeping in mind that the sample consisted of students in various years taking an introductory statistics class, are you worried about bias or confounding variables? Well, you know, I sure am. For math especially, because students taking an intro stats class, they're not representative of the larger population, especially when we're looking at the relationship between year and math SAT. People who are, as the slide so euphemistically puts it, quantitatively challenged, they might put off their stats class, or they might have to take it several times. So when we actually take the sample, they're in their 3rd year, and it's also the 3rd time they've taken statistics. On the other hand, verbal ability isn't really connected necessarily with math ability. So I'm not as worried there. But all of a sudden, I think that p-value of 0.004 for math SAT has been called into question. So, to sum everything up, We, in this video, have been looking at analysis of variance, that's inference for categorical and quantitative variables, with categorical explanatory and quantitative response. We looked at the similarities and differences between several sample and two sample designs. We looked at the notation, the statistics, T and F. We looked at the factors in making T or F large, which tended to be the same for both. We looked at variation among means or within groups, and we looked at F as a ratio of those variations. We talked about how large an F has to be considered, quote, large. One thing that is a factor in how large F is the number of degrees of freedom. The degrees of freedom affect the way that F is distributed. And we talked about the role of the sample size. Then we actually performed some analysis of variance. We talked about formulating the appropriate hypotheses. We looked at creating an ANOVA table by hand. We talked about the F statistic and the corresponding p-values. We talked about that first step in doing ANOVA in practice, which is considering the displays and the summaries. The displays are side-by-side box plots, and the summaries involve looking at the means, SDs, and sample sizes. We talked about how to read ANOVA output, and we talked about the guidelines that must be met in order to use ANOVA.